Let me give an outline of the talk first. So I'm essentially dividing it into two parts, the sphere and the general genus case. So I'll start with the motivation and the definitions. And then I want to talk about the infinite Siegel disk, which is something introduced by Siegel. And then I want to talk about one of the main theorems, which is something I call overfair and the Grunsky theorem in the plane. And the second half is going to be about generalizing to higher genus with arbitrary number of conformal maps. I'll explain what this all means as we go along. And then for the generalization, I have to talk about some integral operators that are due to Schiffer, Max Schiffer, in order to define the Grunsky and something called the Faber operator. And then give generalizations of a Faber isomorphism Grunsky inequalities, and then prove sort of, or at least state the main theorems about bounded overfair and the Graph-Grunsky theorem. So I'll say what all this means as we go along. So we'll start with the Grunsky operator in the sphere. So let's get this out of the way. So just the definitions of the functions and forms that are being used. And then I know when I lower it, some of you in the back won't be able to see it. So if you forget something, just let me know and I'll raise the screen again. So we're going to be working with the Bergman space of one forms. I like to think, for the analyst, I like to think of the Bergman space as a space of one forms, and it's dictated by the way it transforms. You're sort of forced to do that because if you treat it as a one form, then pull back is an isometry and it's very convenient. Sigma here is a Riemann surface, can be quite arbitrary. So we look at L2 harmonic one forms on the surface. You do not need a metric or anything to define that. It can be invariantly defined with the Hodge-Star operator. In coordinates, it'll be the thing you're used to if you don't like Riemann surfaces. And that has a decomposition into anti-holomorphic and holomorphic parts. And those come with orthogonal projections. And the Dirichlet space is going to be the space of harmonic functions now, whose derivative are in L2. Actually, I forgot to say something. I'm always modding out my constants, and I've received a bit of sympathy for doing this. It gets very fussy if you put the constants in. And it's important to put them in at some point, but they're not in this talk. I want to keep things simple. And then there's also the harmonic or the holomorphic Dirichlet space and the anti-holomorphic. Those are anti-holomorphic and holomorphic functions whose derivatives are L2. There is no decomposition unless sigma is simply connected. You can't have a similar statement to this unless it's a simply connected set. And then I use C for composition by F, and then F star for the pullback.
So just sigma is not the sphere here. It could be.
Could be anything.
Because otherwise, there are not many harmonic functions.
What's that?
Otherwise, there are not many harmonic functions. Right?
Yeah, that's true. Yeah, I didn't say it was compact.
Yeah, no, because it was on the sphere in the first slide, I think. But
yeah, but the sphere sigma is not necessarily.
Yeah. Okay. Okay.
There's a bunch of surfaces involved. Okay, so. Let's see. So let me start with the classical definition of the Grunsky matrix. So going way back, goes back to 1939 at least. I say at least because you're always wrong if you pin it down. So the Grunsky coefficients, there's this generating function given by this expression in terms of a holomorphic map, which is one-to-one in a neighborhood of 0. And then you get these coefficients nm when you expand this in a power series at the origin. And then they can be used to characterize univalence, so whether it's one-to-one. So there's a classical result, if reformulate a little bit in modern terms, that F, the mapping function, extends to one-to-one holomorphic function on the disk, if and only if these coefficients form the matrix coefficients of an operator on little L2 with norm less than or equal to 1. So it's a very nice sort of classical characterization of univalence in terms of a norm. It's a little bit fussy if you want me to match it up with L2, little L2, because you have to put in some root k's or something. I will 100% get it wrong. But of course, if you're looking at this, you're thinking there should be an operator interpretation, and little L2 is not that satisfactory. So a little bit of history before I settle on the definition I want to use in the talk. So, and also I want to justify why I'm talking about it here, because you know, it's sort of even my postdoctoral advisor thought it was hopelessly old-fashioned, but that doesn't seem to be the case anymore. So some reasons, the first four are very closely connected. So it arises in the representation theory of diff S1. So you can find this in Kirillov and Yurev's 1988 paper, but it's also implicit in Siegel's 1981 unitary representation paper. And it relates to, again, these are all closely related, relates to polarizations of spaces of Fourier series on the circle, which is something that comes up in the Siegel moduli space picture. So just, Noggin Sullivan first talked about that in 1991. You could say it goes back to Siegel, but in the, we already have these two references here. Tocqueville and Thiot sort of brought it to the modern world in relation to Teichmüller theory, and then some generalizations to higher genus surfaces was done by Mohammad Shirazi and Wolfstow-Lockeny. There's also, this is closely related to the period mapping, so-called Kirillov-Yuriev-Nog-Sullivan period mapping, and you can give, which is an embedding of the universal Teichmüller space into a space of polarizations. And you can use it to give an explicit Kähler potential for the Weil-Petersson universal Teichmüller space. That was due to Tocqueville and Thiot, although it's implicit in some earlier works in the smooth case. I'll say a bit more of that later, and it equals the Libner energy by a result of Yu and Wang. And then, apparently, at the last workshop, there was a talk by Wiklund. So Johansson and Wiklund, and also Courteau, Johansson and Wiklund, have given a relation to the partition function of the Coulomb gas. So somehow it seems that there might be some reason that this would be of interest to at least some people. Okay, so now let me nail down the definition. I'm going to use a classical definition due to Bergman and Schiffer. It goes that far back. It's explicit in the paper. You can find it. They give, here's the generating function for the coefficients, no surprise. That is the integral kernel of a bounded operator on the anti-holomorphic Bergman space, and the output is in the holomorphic Bergman space. And this bar is unavoidable. It's because somehow there is some sort of, well, I'll try to explain, at least indicate where it comes from. But in some sense, if you allow the bar, like Bergman and Schiffer did, things make more sense. This thing here is called the Faber operator, which is, I've taken this, you'll recognize this integral kernel as appearing here. And then we pull back an anti-holomorphic one form on the disk to f of the disk under f inverse, and then we apply this integral operator. And that produces so you let z lie in the exterior of the domain f of d, and that produces a holomorphic one form on the exterior of the domain f of d. Oh, this is, I wrote something dumb here, so this a, that should be ignored. I want to take the complement of the set, not the function space, obviously. So this operator arises in approximation theory. There's a whole literature about it. I've tweaked the form to make the talk more coherent. And it doesn't matter so much, but when it does matter, I'll indicate it. Last thing I want to say is that this kernel function here actually annihilates anti-holomorphic one forms on the disk. This is an identity due to Schiffer, Max Schiffer, and this is his trick for desingularizing the kernel. Okay, any questions up to here? Okay. So,
yeah, I have a question. So just a silly question. So I don't see why the right-hand side is still a function and not a constant. You integrate over z and w, what remains?
You integrate only with w.
oh, I'm sorry. I have a bad habit, I write double integral here when it's in 2 dimensions.
I see.
Yeah, so this is a bad habit from reading classical papers.
Thank
So
you.
I have to break myself of that habit.
So the DZ remains.
The Z remains, yeah. So actually you can, yes. So DZ is there, oh, right. Okay, now this is not a classical thing. So because I want to insist on treating it as an operator on one forms, I want the output to be a one form. So Z remains, and the DZ is part of the output being a one form.
It should not be in the integral. It should be outside.
It is not. I mean, that's why I put the sub W there.
So in fact, in the left-hand side, it should be alpha bar dz bar also. To be coherent with the... On the left of the arrow, it should be alpha bar dz bar.
No, alpha has a DW bar in it.
Yeah, alpha bar dw bar, yeah.
No, but it has a DW bar in it because it's a one form.
So alpha on the right-hand side, but okay.
No, I mean alpha is a one form, so alpha locally would be written H of Z dW bar, or H of W dW bar. Okay, so let me confess that when you try to write the classical formulas in terms of modern differential geometry, there's never a good way to do it. But this has precedent. You can find it, for example, in Einard's lecture notes on Riemann surfaces, so I'm not making up this notation. Yeah, it's kind of, so this kernel here is sometimes called the fundamental bidifferential, for example, in the geometry literature. Okay, so now if you want to talk about this on functions, if we're working in the space, if we're working in a simply connected domain, because I modded out by constants, and it's a simply connected domain, every one form is exact, so I can identify the exact one forms with the function's mod constant. So there's just immediately you have an isometry between the Dirichlet space and the Bergman space, just by conjugating by derivative. Okay, so now here's some results about it. So f is, the mapping function is quasi-conformally extendable if and only if the Grunsky operator is in norm strictly less than 1. That's a result of Kuhnau and Pomeranke. And it's Hilbert-Schmidt if and only if the Schwarzian derivative of f is L2 with respect to the hyperbolic metric. That actually goes all the way back to Gavin Jones. I knew about this paper for a long time, but for some reason I've missed for many years that this actually was originally Gavin Jones. So I've been crediting Shen and Dr. Jean before that. But yeah, no, it's got to be Gavin Jones is the first one. And he also went further to characterizing the Grunsky operators in the Schatten P class in terms of certain Bessel spaces. Now, the next theorem is actually very important for what I'm going to talk about, and that's that this Faber operator is an isomorphism if and only if f is quasi-conformally extendable. So the geometry of the domain relates directly to an algebraic property of the operator. And also notice the if and only if. I'll say something about that in a minute. First, the attributions. The way I wrote the Faber operator, it follows directly from the Paukov-Yumohametov's result back in 97 and 01. But it also follows from Shen and Chabush using some of my results with Wolf-Staubach. Now, the reason for the weird citation is because Shen's statement is more like the classical Faber operator than mine. So I rewrote it so that it would be consistent with the rest of the talk. But I really want to give Shen credit for this result. And they were both independent. And it's actually a little bit hard to interderive the theorems unless you have a couple of extra things. Okay, back to the fact that this is an isomorphism if and only if it's a quasi-circle. This is some interesting thing that characterizes there are many if and only if statements about quasi-circles. And then behind everything in this talk is that it should be done on a moduli space, and in fact on Teichmüller space. So everything I phrase should be phrased so that the seams after you sew are quasi-circles. Otherwise things are of course much easier. Okay, so now I'll talk about the infinite Siegel disk. I'm going to bring it up a little bit. I won't state it in the original form in Siegel's paper about this. I'll use a little bit more modern stuff a little bit later by Nog and Sullivan. You look at the homogeneous H half space on the circle, maybe the nicest characterization on the circle, you just have this, you write the Fourier series because it's an L2 in particular, and the Fourier series have to satisfy this inequality. Because it's simply connected, they're the boundary values of the holomorphic and anti-holomorphic Dirichlet bounded functions. You just do the Poisson extension. You can, everywhere you see e to the I and theta for n positive, you put in z to the n. E to the I and theta for n negative, you put in z bar to the n. And then you get a sort of standard decomposition of the space into positive and negative Fourier modes. And the action by diff S1, in fact, extends to the quasi-symmetries of the circle. This is H goes to H of phi. It gives you a new decomposition. So you look at, the idea is, you come across a disk floating in space, you want to talk about Fourier series, you have to parameterize the boundary. And then you parameterize the boundary with your phi, then you use the phi to decide what your positive and negative Fourier modes, and that gives you a new decomposition, W sub phi, W bar sub phi. So the space of decompositions is acted on by the quasi-symmetries. So this idea, well, I don't want to, again, you can't say who started it, but this appears in Siegel's 1981 paper in the smooth case, and he worked in L2, which actually is not the appropriate analytic space for this class. It should be H1/2 or H dot 1/2. So what he called the infinite Siegel disk, after called Ludwig Siegel.
What's the meaning of the dot? You say H dot? What is the dot?
Yeah, the dot. Did I not write that? So when I wrote mod constants.
Oh, mod constant is the dot.
Yeah, I should have said that when I wrote my thing at the beginning. And I should probably have a dot there and also a dot on the, where's this thing? I should have a dot on both of these probably.
Do you really mean L2 of S1 inside H1/2 of S1?
Yes, I do. Oh, sorry, I mean the opposite. Yes, thank you. H1/2 is better. Yeah.
Okay, so it's the reverse.
Yeah, it's the reverse. Thanks. So we have this map from negative Fourier modes to positive Fourier modes. I just invented this notation because it probably is easy to follow. And you want that I minus Z bar Z is positive definite. Looks like the Grunsky inequalities. Mod Z is less than 1. Z transpose is Z bar. And now the restricted thing, Siegel included the condition that Z is Hilbert-Schmidt. I want to distinguish, if you leave out 3, we just call it infinite Siegel disk. And if you put in 3, we'll call it the restricted, just in line with the representation of the language. So then W sub phi is a positive polarizing subspace in the sense of symplectic geometry. And the decomposition you get is Lagrangian with respect to the completion of this nice pairing. And if you have a smooth function, you can easily check that it's invariant under change of variables. So it's invariant under, by change of variables, it's invariant under composition. I'm going a bit slower than I want to. So more literature. So the quasi-symmetries Nog and Sullivan observed, actually earlier result of Vodopyanov took care of the boundedness essentially. That the quasi-symmetries are precisely the bounded symplectomorphisms of H dot half. So once again, we have an if and only if. So the phi, which act nicely, are exactly the quasi-symmetries. So another score for classical Teichmüller theory. We sort of are forced into this by a sort of modern representation theoretic condition. And this map from phi, Kirillov and Yuryev noted that Z was the Grunsky map. They did this in the smooth case. And Dr. Gentil showed for quasi-symmetries, then you can use this map from phi to the Grunsky matrix. It's a holomorphic embedding of the universal Teichmüller space, which is the quasi-symmetries of the circle mod, the Möbius transformations of the circle, into a space of operators. So, and then David Radnell and Wolf Staubach and I use the generalized Grunsky matrix, which is a classical thing. and we gave a holomorphic embedding of the Teichmüller space of genus 0 surfaces with n boundary curves into an infinite Siegel disk.
So what's the difference?
Sorry?
What's the difference between phi and f in the third line?
Yeah, I'm gonna have to explain that in a minute. So yeah, so this is, I haven't explained this yet, and I'll explain it using conformal welding. The very quick answer, because you asked if you take phi to be the quasi-symmetry, you have two welding maps F and G, you take the F. But I'm gonna do that in a sec. And I just wanna say this last result about the embedding, it requires the fact that the Siegel moduli space, so this Riemann surfaces with boundary parametrizations, can be almost identified with classical Teichmüller space. And David and I showed this almost 20 years ago. It's somehow a really interesting fact that Teichmüller space was reinvented by Siegel without actually being entirely aware of it. Plug for a mini course next week. That'll be the theme of the mini course. So more on the literature. You can also restrict to the so-called Weil-Petersson universal Teichmüller space, which is a sort of little bit newer thing. Dr. Giannattio also showed that that is a holomorphic mapping into now the Hilbert, between between a Hilbert manifold and a subset of a Hilbert space. They also showed this is a Hilbert manifold, although this was initially due to Puig. And it's a Kähler manifold, and this is a potential. Again, involves explicitly the Grunsky operator. And the form of the potential in the smooth case actually appears in Kirillov and Yuryev, and also Hong and Rajev. And you can sort of get it by thinking about what symmetric space it's embedding to. It's sort of like a standard infinite dimensional space, and so you can guess what the Kähler potential should be. But the rigorous proof is due to Dr. Giannattio. Okay, so now, what's this all about? Let me now talk about the conformal welding. I somehow feel that my pictures are not up to the standards of a probabilist conference. I am officially throwing in the towel with this picture. So let's say you have, so conformal welding, it goes back to Pfluger in 61. Many people ascribe it to Kirillov. Kirillov did some kind of proof in the diffeomorphism case, but I recommend scrutinizing it. So if you have a quasi-symmetry of the circle, then there's quasi-conformally extendable conformal maps from the disk into the sphere, and from the outside of the disk into the sphere, such that phi now factors as G inverse of F. And so this is now the map from phi. You can see it this way. You sew the surfaces to, you sew the surface to a cap using phi, you uniformize in a sense, or I would say solve the Beltrami equation, and then you get a sphere with bounded by with some quasi-circle seam. Now the idea is, the idea of this talk is that you have this formal operator which is composition by phi, which acts on the polarizations, but I would like to interpret the polarizations in terms of boundary values in the sense of Graham-Siegel. So you start with a holomorphic function here, and you want to pull it back to the circle under F. F here is now the boundary parametrization of the Riemann surface. So I want to literally pull back the boundary values. I don't want to have a sort of formal pulling back. I want to show that you really can just pull back the boundary values. So it takes a little bit more work. So then we have this process called overfare. So if you have a Dirichlet bounded harmonic function on omega 2, and you say you have gamma here, if gamma is sufficiently nice, I'll say exactly in a minute, then you can take the boundary values to be in h1/2 of the boundary of omega 2. I'm sweeping some subtleties under the rug. You need to treat that boundary as an ideal boundary, which in the simply connected case just means you map it to the disk and treat the circle as the boundary. And the boundary values exist non-tangentially if and only if they exist pulled back to the disk non-tangentially. On Riemann surfaces, you do something similar, but you phrase it in terms of the double. But then there's a subtlety, is that on it, you want to now say that these continue to the other side. You solve the Dirichlet problem on the other side with these so-called h1/2 boundary values. And you get a Dirichlet bounded harmonic function on the other side. So the theorem is there exists such a bounded overfare if and only if gamma is a quasi-circle. And now I've left out a bunch of details because I don't want to burden the talk with the technical details, but I just want to indicate them. So you want to say what you mean by the boundary values. So you want to say that they exist non-tangentially. You say they exist non-tangentially if you pull back to the disk by treating the boundary as an ideal boundary. But the ideal boundary from one side of the curve is not the same as the ideal boundary from the other. This is not such a subtle thing, but this is the way it is. And why should h a half on one side be h a half on the other? In fact, it's even worse than that. There's a theorem that goes back to Alfors and Berling in the 60s that it's not even an absolutely continuous transformation. So a set of measure zero, Lebesgue measure zero, meaning the image of Lebesgue measure zero under the circle, is not Lebesgue measure zero from the other side. So quasi-symmetries are not absolutely continuous. They do, if you transform Lebesgue measure with quasi-symmetry, it's not absolutely continuous. And this was discovered independently very recently by Bay and Zinsmeister, but they also added an assumption that the curve is rectifiable, in which case it's quite a bit easier to talk about the boundary values. And this is the subtlety here I was talking about. You have to do a little bit more. You use a classical theorem of Berling and you use capacity instead of Lebesgue measure. So
when you say one cannot say that they're the same, are you saying they're different, or are you saying it's not obvious that they're the same?
I'm saying it almost doesn't have meaning because when you talk about the h a half space, everything is equivalent up to sets of measure zero. But sets of measure zero on one side are not sets of measure zero on the other side. So I don't even know, I can't say it's true or false. I mean, I could just say they're not equal, but you can't quite compare them because the sets of measure zero are different.
I thought they're defined on outside of sets that are much smaller than measure zero.
Yeah, so then what you need to actually do for h a half, like the Sobolev technology doesn't do that, you just beef it up very slightly with some capacity. You can say that the boundary values exist up to a set of logarithmic capacity zero. That is preserved by quasi-symmetries, and then you're okay.
And then this equality happens to be the bottom one.
You should really say,
the bottom line.
but h1/2 isn't defined in terms of that capacity, so so you have to define a new space which completes h1/2 a little bit to more sets, and those are equal. So, yeah, I'm always tempted to sweep this under the rug, but then people think nothing was done, so I wanted to. So, okay, so how am I doing for time? I think I'm way better.
Half an hour left.
Yeah, okay. Okay, so what I want to do, maybe going back to this picture, maybe it's better if I don't. Oh, I went too far. Hang on. I'll show that picture in a second. So what I want to do is make sense of the pullback of the Dirichlet space on the omega 2. That's the complement of the image of F, the parametrization. So you pull it back to the disk. This doesn't quite make sense because F maps into omega 1. Let me show you on the next picture. We've got omega 1 and omega 2, and F is going to map into omega 1. So we take the harmonic function, or take a holomorphic function on omega 2, and we want to pull it back to the circle using something that's defined on the other side. So one needs, keep hitting the wrong thing here. So what we do is we insert, first of all, the Faber operator, which you'll recall is an isomorphism for quasi-circles. And then you apply this overfare operator to make the domain, or to make the set of the functions lie in the right space, so now I can pull them back under F. And so this is the way of sort of pretending you're pulling back the boundary values under the boundary values of F. And it literally is doing that thanks to some of these theorems. And so now if omega 1 is a quasi-disk, then the projection, you pull back the boundary values. I've inserted this isomorphism here. And then you overfare, and then you pull back the boundary values using overfare. You project onto the anti-holomorphic part, you get the identity. You project onto the holomorphic part, you get the Grunsky operator. So in particular, that means the pullback of the boundary values of holomorphic directly bounded functions in omega 2 are the graph. It's precisely the graph of the Grunsky operator. So this describes your new polarization, your new set of positive modes in the Fourier series. We also later got a version of this for half-order differentials with Peter Crystal and Wolf Staubach, and the polarizations there are orthogonal, not symplectic, so it's more related to spin geometry than symplectic geometry. Okay, now let me illustrate the theorem with some pictures. So we have in the Graham-Siegel picture, you have some holomorphic function of bounded Dirichlet energy on omega 2, and then you get the boundary values in some space, which I'm sweeping under the rug a little bit, and then you overfare to the other side. Then you pull it back to the disk, and this will give you the set of things which came from holomorphic functions in omega 2, and that is, oops, what is that? I wrote the presentation. So this gives you the image of identity plus Grunsky matrix is a set of possible values. Okay, let's see what happens. Okay, good. Now let's move on to general Riemann surfaces. I think I'm doing okay. Maybe let me just pause. I don't want to go too fast. Oops. Are there any questions about this before I move on to the next part? Okay. Let's talk about it for general Riemann surfaces. What do we need to do this? So we need generalizations of the integral operators to define the Grunsky and Faber operator. We need a bounded overfare theorem in the case of the surfaces. The Faber operator should be an isomorphism. And to formulate this on one forms, which is another thing we did, you need to take into account the cohomology of the surface. So let's start with that. I'll start with the operators. So here's the picture in the upcoming definitions. And actually, you can do this, you can even use Jordan curves, at least for the definitions of the integral operators. Just actually ignore this line. That's a holdover from another slide. Just ignore that. I'm sorry. It doesn't belong. You can actually have quite general pictures where you divide this into disconnected pieces, as long as you have a consistent way of deciding what is on one side of the curve and the other. Callis said I should call it a bipartite graph.
Sigma 1 and sigma 2 don't need to have the same topology, I guess.
The same? Oh no, yeah, they don't. Yeah. Okay, I made a bad picture, but there will be other pictures. Yeah. They do not need to have the same topology. So the operators which go back to Max Schiffer are, you take the second derivative of Green's function, you have two natural choices, dz dw and dz dw bar. You integrate them against one forms. By Green's function of the compact surface, let me just show you, the compact surface is the whole thing, so that you use Green's function on the whole surface. So this is the set, the function which has two logarithmic poles of opposite sign. That defines it up to a constant, which I can ignore because you're differentiating the kernel. And then you also have something related to the Bergman kernel. So this here is called the Schiffer kernel, and this here is the Bergman kernel. And although the terminology is not consistent in the differential geometry literature, please watch out for that. And then you integrate the one form against the kernel function. So then, in this case, we get anti-holomorphic one forms go to holomorphic one forms on one or the other piece. So you can either stay on one piece or traverse across. Yes?
What is the operator R?
Yeah, I was going to say that in a second. So this is this one here, you mean, right?
Oh.
Is that what you're asking? Just restriction.
It says G, the Fourier function of R.
Oh, yeah, that's the Riemann surface. So compact Riemann surface.
That's the standard Riemann surface. Not partial, the Fourier function of the
I guess, yeah. I mean, I was defining it in the hands-on way, that it just has two opposite logarithmic poles, and that defines it up to a constant, and it's harmonic. So, yeah. And there's no boundary, so that's enough. Because you're taking the whole surface. Yeah, and sorry, yeah, I made a mistake here. That should also be a math script instead of a math cal. Okay, so we get this Bergman operator and involving the Bergman kernel. And actually, this is the adjoint of the restriction operator from the compact surface to one side. And actually, I could not find that in literature anywhere. Schiffer didn't seem to notice, which is very odd to me, but it seems to be true. Okay, so some history. Let me just check the time. I think I'm still doing okay.
Minutes?
So these arise in geometric function theory, and they're related to the theory of conformal maps, Clemens sequential jump formula, Grunsky inequalities, blah, blah, blah. So in the plane, it's Bergman and Schiffer and various publications of Schiffer. Multiply connected case of Schiffer, Schiffer-Springer. When the outer domain is not a sphere, so not necessarily compact, again, Schiffer. And then on Riemann surfaces, there's a book of Schiffer and Spencer from 1954. An almost unreadable book, but it has a lot of good stuff in it. Unfortunately, it's because it's very hard to read. Okay. So now talk about the Grunsky and Faber operator for functions. So we conjugate by D, and then we pull back the T11 operator. That should be an upper star there. Conjugate by F, and then conjugate by D. And actually, if you go back to the original expression on the almost the first slide, and then do a little bit of work, this definition reduces to the original one. Now the Faber operator, you do the same thing with T12 now. So this maps from one side, you start here in the disk, anti-holomorphic functions in the disk, and it maps into holomorphic functions in sigma 2. And now the way I describe this takes one forms to one forms, and you have to ensure that the output is exact so that you get functions. And you need this condition here. If you restrict to the orthogonal complement of the restrictions anti-holomorphic one forms on the compact surface, then the output is exact. So that's part one of taking into account the cohomology. So if you want, in brief, conjugate the operators by F and differentiation. And in the case of the Faber operator, you have to do a correction for the cohomology. Okay? And now I want to talk about the Faber and Grunsky isomorphisms for functions. This was proven by Mohammad Shirazi in his PhD thesis and published in 2020. If you have that sigma 2 is connected, and the images of the F's are quasi-disks, then this T12 map is an isomorphism from this orthogonal complement, this corrected orthogonal complement, into the exact one forms. So this generalizes the theorem that I gave to Shen and Nabokov and Nurmagomedov in the sphere. And then, in particular, because conjugation by D and F are isomorphisms and even isometries, then the Faber isomorphism is Faber operator is an isomorphism. And furthermore, you get Grunsky inequalities. It's bounded by 1 if you have quasi-circles. So we have the first part of trying to get the Siegel disk in the case of higher genus surfaces. And again, I want to remind you of you can express this bound as being that I minus Grunsky bar Grunsky is positive definite. Any questions up to here? Yes?
Can the loops be arbitrarily close to each other? There are many loops. The loops can be arbitrarily close to each other.
So I should have said, yeah, the condition is that the boundaries are quasi-circles, and just the quasi-circles themselves cannot intersect. So they can be arbitrarily close, but not touch. I should say there's a theorem of Chiara-Theodori that the mapping function extends continuously to the circle just by virtue of being a conformal map. So another way to say it is you take the closure of the image and make sure the closures of the image don't intersect. Okay? So now now I want to talk about it for one forms, and somehow I want to talk about this cohomological correction. So now let's say, now we have this picture like in Graham-Siegel that we have a Riemann surface with a number of conformal disks and conformal maps into those conformal disks. So in one of the models of the Siegel moduli space. So any L2-1 form on, I should have said on the compact surface now, it has precisely 2G independent handle periods. So, and then by the Hodge theorem, every cohomology class has a unique harmonic representative. So you can get all the possible periods with harmonic 1 forms on the compact surface. And then those decompose into the periods you get from holomorphic 1 forms on the surface and the periods you get from anti-holomorphic 1 forms on the surface. Now, there's an interesting fact. Once you remove the disks, you can actually achieve all possible periods on this open Riemann surface without a problem. So you can achieve them with holomorphic 1 forms. So when you remove the disks, you get much more flexibility in what the holomorphic 1 forms are. And so now you can think this in Mohammed's theorem, we got rid of, you can see that we got rid of some of the holomorphic, anti-holomorphic periods in order to map onto exact things. And you can ask what happens if we insert those back in. It turns out if you insert those back in, you get all the periods which would arise from anti-holomorphic 1 forms. They now appear as periods of holomorphic 1 forms. There's some interesting switching in the cohomology that goes on, which I don't know, might be interesting. I keep thinking it sounds like things people have told me about. But then, okay, so now this is the precise statement of what I just said. If you put all of the anti-holomorphic 1 forms back into this operator, sorry, that should say T12 there, both of these. Then that spans the anti-holomorphic cohomology classes, but all of these output forms are holomorphic. So you can get, it's a little confusing, but the anti-holomorphic periods you get on the compact surface can be achieved by holomorphic 1 forms on the surface with the disks removed. And then you also get that if F maps into quasi-disks, then you can define this sort of generalized, kind of like a Grunsky operator. I'm removing the Fs to keep things simple now. I don't want to clutter it too much. So you take, so we use this isomorphism to get almost all the possible 1 forms, so an infinite dimensional space, plus all the cohomologies from anti-holomorphic things. And then you have to add in the remaining cohomology just by restricting things on the compact surface. When you do that, this is a new Faber operator on this map onto the semi-exact 1 forms on sigma 2. By semi-exact, I mean they have 0 boundary periods. You can also use that to get approximation theorems on L2-1 forms on Riemann surfaces. Okay, any questions up to here? I gotta crank up the AC to get more questions. Okay, then you get a Grunsky inequality for 1 forms. So somehow this is the natural Grunsky-like object. You'll see that if you want to produce all possible polarizations, you have to add in this holomorphic correction, holomorphic to anti-holomorphic. And when you do that, this operator is now bounded and normed by 1. So that gives you sort of Grunsky inequalities. And all the Grunsky inequalities you get for genus 0, one boundary curve, genus G, n boundary curves for functions forms, they all sort of follow from this one. And this inequality itself comes from one row and the unitarity of a certain scattering matrix, which I find very interesting. So you have finite polarization, and then it sort of fits in the standard picture, but there's some associated unitary matrix. Okay, so now I want to talk about, so that was the formal description of the polarizations. Now I want to again make this literally make sense in terms of boundary values. So I need to do overfare on general genus surfaces. So now you take a compact Riemann surface and you separate it into two pieces by a complex of quasi-circles. You don't need the pieces to be connected. You can do all kinds of complicated things as long as every quasi-circle has two sides. You just have to label two groups of connected components. And if you start with a harmonic function with L2 derivatives on sigma 1, that has boundary values in a certain h1/2 space. Again, you have to do some work. And then you can solve the boundary value problem on the other side and get a harmonic Dirichlet boundary function on the other side, which we call the overfare. And so the process is kind of simple. And first of all, no matter how you divvy up the surface, as long as it's quasi-circles, there's a unique H2 on the other side whose boundary values agree in a fairly strong sense. And if sigma 1's connected, then the overfare is bounded. I wonder if anyone can figure out why you need that it's connected. So I had a conversation about this with someone. I don't know. It's sort of interesting to think about. It's related to the fact that the Dirichlet norm does not detect constants. And so if you think about that, you'll see that we need the originating surface to be connected. Okay, so we've also shown this for one forms, but one needs to take care of the cohomology. It's a little fussy, so I don't want to put it in the talk. And then we had an earlier result, which doesn't quite fit in this picture, where you can divide general surfaces on either side. This is sort of okay, we had an earlier result just for one curve in the surface. Okay. And then Mohammed showed that the graph of Grunsky theorem holds in that case. So you have n maps into quasi-disks in a genus G surface. You pull out the boundary values of the inside surface sigma 2, and it's the graph of the Grunsky operator for functions. And then we also have a version for one forms. You pull back the Bergman space of one forms on the inside surface under the mapping functions on the other side, and that's the graph of the Grunsky operator for forms. I put O hat here because you have to put some cohomological correction again in. At the end of the talk, I didn't want to cram that stuff in, but it's fussy but natural. It's fussy at 2:50 in the afternoon, but it's pretty natural. So if anyone wants to see how it's done, I can show you some other time. So I'll just end with some pictures to sort of show how this goes. So now I just want to completely talk about the Siegel moduli space picture. So imagine you have a Riemann surface sigma 2 floating in space. You want to talk about the Fourier series on the boundary curves. So you parameterize the boundaries with some quasi-symmetries. And then that tells you how to sew on disks to get the other version of the Siegel moduli space picture. You sew on the disks, and then now you get a number of conformal maps into open subsets of the compact surface. So now you have boundary parameterizations by conformal maps, which are equivalent to the original ones. This is conformal welding, essentially, but on the surface. You start with a holomorphic function on sigma 2, which is Dirichlet bounded. Take its boundary values, pull it back under F. Take its boundary values, solve the boundary value problem on the other side, apply overfare, and now pull it back under F, and you get a new polarization on the space of harmonic functions, which is actually the graph of a Grunsky operator. Okay, so let me just summarize now. So we have an infinite Siegel, this picture of Siegel, and it extends to arbitrary genus and boundary curves. And that picture also plays a role in the determinant line bundle defined by Siegels in his 80s preprint. The full definition appears in Iji's book. By full, I mean it's implicit but complete. So whereas Siegel's definition was kind of a sketch, Iji's actually worked out a definition which tells you what it is, though it's not explicit. And I want to mention that when Iji defined it, he also, quite naturally, just thinking about using the harmonic analysis, ended up with the same H1/2 space, which at the time he was using analytic parametrizations, but then the Knox-Sullivan result tells you that quasi-symmetries are natural to use because they preserve that space. So everything sort of comes together quite perfectly analytically when you think it through. Last thing I want to say is that this Grunsky matrix that we have, the general one, unifies the classical period map, the one that goes all the way back to Riemann essentially, and it unifies it with the Kirillov-Yuryev-Knox-Sullivan period map.